Next, we're going to look at continuous compounding, and I alluded to this at the end of the previous lecture. But to motivate this, I'm going to consider this first example. Consider $1 invested with interest rate 100% per year. Yes, that is 100% per year, so you earn $1 a year. If it were simple interest. Compounded m times per year. Well, how much is in the account after 1 year? Maybe I should have written that. How much is in the account after 1 year? Well, we'll use our formula, the one with r over m and so on. Well, we start with 1. Battery power is low. 1 times what? 1 plus 100%. I'll write it as 100% over m to the m times 1 year. What does this equal? Well, it's 1 times 1 plus 1 over m to the m, which is just 1 plus 1 over m to the m. So right here, what we're really going to be looking at here is what happens as m gets larger. We're looking, so in the last example in the previous video, we said we had daily compound, we had monthly or annual compounding, quarterly, monthly, and daily. And here we're going to wonder what happens as m gets large. So this is the amount after 1 year. It simplifies to 1 plus 1 over m to the m. Well, what happens if we have one compounding period? So here we'll look at this chart. We have an m value, the number of times we're compounding per year. And here we have in the right side the amount in the account after 1 year. So the yield of that $1 after 1 year. Well, if m equals 1, this equals just 2, this quantity, 2.000. If m equals 10 compounding periods per year, what do we get? We get 2.59374 ... If m equals 100, what happens? Well, we get 2.704813, and so on. What if m equals 1,000? Well, notice, in going from 1 to 10, it went from 2 to 259. When going from 10 to 100, it went from only from 259 to 270. Going from 100 to 1,000 compounding periods, it goes from 270 to 271. 6924. And going up to 10,000 periods, it goes up to 2.718280, and so on. But as m gets larger, this amount in the account after 1 year approaches a finite number. And it approaches a number that you may have seen before somewhere. So this number, 2.71, it's not going to get much larger than this 2.71. But I will tell you, as m gets larger, this quantity approaches a value called lowercase e. Lowercase e, the base of the natural logarithm. So back in algebra, when you learned logarithms, they said, we have all these logarithms with any positive number as its base. But then there's this one other one that gets its own, its own notation for the logarithm, and it's the natural log, the ln, which has base e, and it's about 2.719 and so on. But this chart shows us that if we keep throwing on compounding periods, if we keep throwing compounding periods into our interest accumulation, having a lot more compounding periods isn't really going to change it that much, versus a few compounding periods. Just look how close 100 compounding periods per year, how close the yield from 100 compounding periods per year is to the one with 10,000 compounding periods per year. But in the limit, so this is not a calculus class, we're not going to do anything with limits. As m goes to infinity, as this m value gets larger and larger, the amount in this account does approach e. So let's define that a little more formally. Definition: continuous compounding is the method of, let's underline continuous compounding, of calculating interest that yields what regular compounding, what compounding, or sorry, what compound interest tends toward with more and more compounding periods. So here, in my notes, I wrote compounding per period, with more and more compounding per period. I guess I like this one more, with more and more compounding periods. And we can't, just let this m value get large, but we can use some results from calculus to give us a formula for continuous compound interest. So we have this formula for continuous compound interest. Principal P at annual interest rate. We'll just do this with annual interest rate. If I'm going to play around with rates, it'll be for general compound interest, not for continuous compound interest. For principal P at annual interest rate R, compounded continuously, meaning we're letting the number of compounding periods go to infinity. We're letting m get larger. Given all that, the balance after t years, balance A after t years is equal to P times e to the RT. And that parallels the second compound interest formula if we just replace that inside rate with e, as we saw in that chart. We saw that tended toward e. So let's look at a couple examples. Example: given annual interest rate of 10% compounded continuously, how much is $1,000 worth after 1 year? How much is it worth after 5 years? Well, we're gonna use our formula. A equals P, which is 1,000, times E, which is a number. On your calculator, you can find E using a second function natural log. It's also equal to like 2.719 or something like that. Well, it's not equal to a number you can read in finite time, but it's close to 2.719. We have 1,000 times e to the r. Annual interest rate is 10%, so to the 0.1 times the, let's make that 1 a little bigger, times 0.1 to the, or raised to the 0.1 times the number of years, which is 1 here. And this is approximately equal to $1,105.17. I think I've been bouncing between approximately equal to and strictly equal to. You don't have to, with banks, they're not going to say you have $1,105.17.936. They'll just round it to near cents. So, it is an approximation, but it also technically is kind of exact. And how about after 5 years? Well, A equals still 1,000 times E to the 0.1. It's still a 10% interest rate, but we're looking at 5 years now. And this is approximately equal to $1,148.72 cents. Oh, I didn't square that properly. there is actually a reason I didn't square that properly. My pen ran out of ink, so I'm 11.48 and 72 cents. This is a special pen that works on this contraption. So right here, you could see what I'm writing on for the last part of this video. It actually ran out while I was writing the definition. So you can see at the beginning of this page, continuous compounding interest did, the ink almost worked there, but for the rest of it, I just have to look at the indentations my pen's making. But that's okay. I'm gonna have to see if they have more of these ink things, because you can't just use a regular pen on these expensive contraptions. But let's look at one more example, and this one will just compare daily compounding to continuous compounding. Example: consider $1,000 with annual interest rate 5%. Part A: how much is the investment worth after 1 year if battery is critically low? I should have time, but now I lost where I wrote if. There's if. If what? Interest is compounded daily. That's part A. Part B: compounded, same thing, compounded continuously. And here we're going to round to the nearest cent. But for daily, for part A, well, we use our compound interest formula. 1,000 times 1 plus. Here I'm going to use the things that are all in annual rates, because we're given everything annually. But we do have daily compounding, so there are 365 compounding periods there. So we have 1 plus 5%, so 0.05, divided into the number of compounding periods per year, 365, raised to the number of compounding periods per year, times the number of years. So 365 times 1 is our exponent, and this is approximately equal to 1,051 and 27 cents. And let's look at continuous compounding. Well, we have 1,000 again times, oh, I don't need times like that. Part B, we have 1,000 again times e to the RT. Well, that's R is 5% per year, so 5%, 1 year. So 0.05, 5% written as a decimal, 0.05 times 1, and this is approximately equal to 1,051 and 27 cents. If you write out the decimal more, this one is slightly larger than the previous one, but do note that daily compounding, continuous compounding may not necessarily give that large of a difference, especially with a small rate or a small amount. And you can kind of see that in that chart at the beginning of this video with m in the left column and 1 plus 1 over m to the n in the right column. As that number kept getting larger, you can imagine where 365 is in there. It'd be like 2.71 or something. So as it gets larger, continuous compounding, if you have an investment with daily compounding, continuous compounding, you should opt for the continuous compounding at the same rate. But in general, it won't give too much more than, say, daily.